All right, so just as a recap for folks who are not physically present, we've got some bounties working on, if you want to go ahead and build an application for the RISC-0 zkVM, we'd appreciate it. And our other bounty out there is crate support, so anything that uses serialization or deserialization crates in the guest, we'd love to support more serialization and deserialization. So first things first, let's make sure you're all on the Wi-Fi. If anybody hasn't connected, we're going to be downloading in just a few seconds, so you want to go ahead and get onto the ZK Hack Open Wi-Fi. So, and if everybody's there, just a quick review. What we're going to cover today is first getting to know the zkVM. I'm just going to go over a little bit about what happens in the guest and host, about creating receipts, and about how we built our zkVM and how it might be different from some other systems out there. We're going to get you started on your first RISC-0 project. We're not going to build you from start to finish here. It's just going to be getting you started, but we will walk you through a simple example. And then at the very end, I'm excited to introduce Bonsai, our upcoming proving system. So, to get us started, we've got a couple of different approaches to writing ZK. And the first one is a direct approach, where we have language that's compiled to produce an arithmetic circuit. And then that newly built circuit is going to operate on inputs and generate a proof as output. So if you note, the direct approach is going to give you a custom circuit, which can be useful, right? It's customizable, but we like using the zkVM approach because now instead of being in the business of circuit generation, we can compile RISC down to an intermediate representation that we can run on our VM circuit. So the program itself gets treated as input to the VM circuit. And this means we can use the same circuit roughly for every program, which is what we mean by general purpose. So before we continue, I just want to talk a little bit more about what it means to use the RISC-V instruction set and what it means to be general purpose. So the RISC-V instruction set, for folks who aren't familiar, it's an instruction set architecture, which is an abstract set of computer instructions. And we like it because the instructions are simple, they're stable, they're open, they've been around for a while, and they've got a lot of eyes on them. So they've had a minute to have a lot of the kinks worked out. So now we're able to write Rust code because it can compile down to RISC-V instructions. And then when we say our program is treated as circuit input, what we mean is we've got RISC-V instructions, we can operate on RISC-V instructions, we can use the same circuit for every program, and what that means for you today in this workshop is that you don't need to write circuit code and you don't need to read circuit code. You're going to be working entirely in Rust. So as we dive into the zkVM, just want to get a few preliminaries taken care of. We're going to be working today in Rust, so if you don't have Rust, you want to go ahead and install that. And then we've got a Cargo RISC-0 tool here that should automatically set you up with a starter template project. And if you want to take a moment to follow these steps, if you have any difficulties, just go ahead and raise a hand. We've got a few engineers here that can walk around and help folks out. But if you'd rather just listen for now, this information will be available later. It just takes a few minutes to do the initial build, so we recommend getting a head start. And while folks are getting that set up, in just a moment, I'm going to talk to you about proving with a virtual machine and generally how our system operates. But I want to give folks time to And then while folks are doing that, I'm just curious, how many people here have worked with Rust before? Awesome, okay, we've got a good number. How many people for here it's your first time working with Rust? Great, okay. And so one nice thing is that this actually is a reasonable way to learn Rust if you're also working on this project, because you can just write Rust code. And so if you're new to Rust, just writing a little bit of Rust, some of the pieces today might not make sense, but we're excited to support you anyway in it. So I'm excited to see you here. Anybody, I want to do the same show of hands here for folks who has already played with the RISC-0 zkVM. Okay, good number of people. Luckily, our engineers seem to have already played with it. A couple haven't, I'm a little concerned, but anybody who has not played with the RISC-0 zkVM, engineers that want to explain themselves? Okay, awesome. All right, so now that I've stalled, it looks like the typing has slowed, so I'm gonna move to the next section here. So proving with a virtual machine. The big picture is just like a regular VM. We've got a host, we've got a guest. The guest is going to run the core work to be proven, and then the host is going to prepare appropriate inputs and react to the outputs, which in our case is a receipt that we've run the code we said we'd run. So with the host code, anything you don't need to be a part of the proof, you can go ahead and run on the host. So any code that you don't need to prove the execution of. And where this differs is, unlike a regular VM, our VM is going to generate a computational receipt. So this is the zero-knowledge proof part. And that receipt today is going to return right to the host, and we're going to check it in the host. But in general, you'd be sending that receipt on to other parties, making it publicly available, whatever your application needs. So to get us started, we're going to take another look into what a receipt is, since this is what you'll be passing around once you're done with your program. Everybody's computer okay? So the receipt consists of a journal and a seal. So the journal is where you're going to record public outputs. And just to let you know, this is zero knowledge, so nothing is public by default. So anything you operate on, if you want it to be public when it's done, you're going to have to write it to the journal. And then that means you get to choose what outputs you're making public using a command that we're going to cover in a few seconds. And then the seal demonstrates that the receipt is intact. It shows that the journal is, in fact, the output of this program whose hash we've included in the seal. Hash with a little bit of a hand wavy there, but. So now to get into our example, we're going to go through for our example, we're going to do a basic proof of factorization. I'm going to prove to you that some number is composite, which means that it's created by multiplying two integers, both of which are greater than 1. So we're going to make a zero-knowledge proof for it, and we're going to be writing a program, or I'm going to be showing you a program that multiplies two non-trivial integers and then produces a receipt. So in the receipt, just to refresh, we're going to share to our journal that composite number that we create using the program. So that'll be the part that'll be the public output. And what won't be public is the numbers we multiplied, because we're going to be multiplying those inside of a guest program. And then the receipt tells us our program ran so that we know the number is composite because we ran a program that multiplied two numbers. Right? So to get to know our starter template, oh, yeah. I can stop leaning here. All right. Maybe. Yes. Okay. I am just making sure that this is fully accessible. So apologies for briefly explaining factorization. Making sure I'm not going to drop anything here. I appreciate you. Okay. So what does this actually look like? You probably want to know. If you're writing code, just to refresh, you're going to be writing guest code, which is the code that will actually be part of your zero-knowledge proof. You're going to be sending input data to the guest for it to operate on, and then you're going to be doing something with that result, with that receipt when you're done. So just so you know, with our upcoming Prove It service, you're just going to be writing guest code, so you don't have to worry about any input data. You'll just be passing that in as parameters, and then the results are going to be made automatically available to you. So for now, we're going to handle all three in our examples, and for any projects you're going to be building over the weekend, you'll be taking care of all three of those. And this is kind of our first look at the guest code and what that looks like. I'm going to be highlighting a few pieces of this, but I'm just going to take a few seconds and let you take a look. Loading a few values in, making sure neither of them are trivial, computing the product. All of that's taking place in the guest. So some pieces to note. We're going to be grabbing inputs from the host. When we're done with our result, we're going to be committing it to the journal. So this has to happen explicitly. So as you go ahead and write your own programs for the zkVM, remember that none of your results, none of your output are automatically public. So you're going to be making choices about what you want to make public and what you want to keep private. Right? And that being able to make those careful choices is a really important part of writing a program. So even though it's just basic Rust, you still need to throw in, the right decisions along the way. And another piece to note is that data needs to get Another piece to note here is that when we're checking this, if you panic, you're not going to produce a receipt. And this is actually pretty useful. If I am writing a program and I have a receipt, that itself is proof that I've successfully executed. And so a panic is informative, right? In cases where you just want a binary, did it work or didn't it work, and you don't need to know the particular error that was thrown, you can just make the thing panic, and then you don't get a receipt out. And so now I'm going to be going into sending inputs. This is host code. So previously we were looking at code written from the guest. This is code written for the host. And some pieces to note here. You have to serialize data to send it to the guest. So that's what this piece is doing, this library. And because data has to be serialized to the guest, that's why we have one of our bounties out there, so we can get more data available as guest data. Few pieces to note. This type that we're using, it's going to be the same type that the guest code reads. So as you share values with the guest, you're going to want to make sure that you're reading the same values in to the guest. When you commit values out of the guest, you're going to want to make sure that you're reading those back out from the host the same type. So just make sure your types match as you go. Yeah. Yeah, this is our serialization and deserialization library. So you'll be able to serialize and deserialize with this in the host, and this just is how we are able to get data into the guest and get data back out of the guest. From the host to the guest. Yeah, host to guest, guest to host. We've got our own, but it's standard Saturday format. Totally. Do you have another question? Okay. So another piece here. So this add input U32 slice is the basic way we're going to send data to the guest. So we've picked two numbers, and now we're sending both of those values to the guest. And just a quick recall, I want to pull you back into this guest code. Then we went ahead and read those, multiplied the values, and committed it back to the host. So sorry to jump around. After committing, just want to point out the last step here, reading the journal. So here, we're going to take the same U64 value we committed, which is the composite number, read it back out, and make an assertion here that this number has, in fact, been produced as the product of two non-trivial integers. So now I want to talk about where you're going to be modifying code, because this full example, it's available, it's part of our examples, it's not that far off from our starter template, but what you've just downloaded has a pile of to-dos, and I just want to go over them so that you know how to get from there to the program that you're going to be writing. So There's 10 to-dos in the template. 7 of them are minor and cosmetic, like update the README, use a license you're happy with. But the 3 non-trivial ones cover the points we've just been discussing. So you're going to be writing code for the guest, you're going to be communicating input data to the guest, and then you're going to be doing something with the results in the receipt. So let's go over the to-dos real quick. Aside from the major items, there's a few to update the README, rename your guest program, add to gitignore if you want. But for the most part, they're pretty straightforward and mostly around writing guest code, communicating inputs, and then using the outputs. And just as one final, oh yeah. Oh, my screen's on the fritz. I'm so sorry. Okay. Was everybody able to see the last few slides, or has it been on the fritz? Okay, good. All right. So this next bit, I just want to add in one note because that last example was pretty simple. If you're going to be, oh boy, I better not touch this now. Okay, so the last. All right, we're just going to ignore that for a second. So the last example was pretty trivial. It just had single values coming in and out. You know what? All right, last example was pretty trivial. We just had single values coming in and out. You're going to, okay, you know what? I cannot explain this. All right, so the last example was pretty trivial, but in general, if you want to get input and output, you're going to want to use structs. And so if you want to pass in a whole lot of input, you want to create a struct, pass that in, probably create a common shared library, and if you're going to get a lot of complicated output out, you probably want that as a struct because everything just gets written to the journal. It's up to you to interpret what comes in and out. Easiest way to do that is with a struct in Rust. And that's just a pro tip to make your life a little easier as you go from this trivial example to a genuine program. And if this wasn't incredibly glitchy, you would see a simple example with that, but I welcome you all to take a look at our examples. We've got plenty available that demonstrate this. And you can find those in our main repository now, I believe. They're in RISC-0 zkVM under the examples folder inside of that. And we've done that so that you can go ahead and give those a try, and they're up to date with our most up-to-date version, which we just released. So all the examples should be functioning there. Give this another try because I do have a lot of pictures coming up. Okay, so I'm now going to be talking about our proving service with no pictures. Okay, nope, we got pictures maybe. All right, let's see if we can get this to work. Come on, buddy.
Maybe while this is finished having its seizure,
There.
can I just ask, how does the guest now relate? Now we learned that example before. How does the guest, where does the guest fit in? Because when we heard about the guest at the start, I'm just trying to understand how the guest now fits into the program that we just wrote.
Oh, totally. Let me go back actually, and hopefully this isn't too glitchy, because that's a really important part. The guest code is, okay. The guest code, imagine, the guest code is code that takes in the 2 values that we're going to multiply together, produces their product after checking that neither one is 1, right? And then commits that result publicly to the journal. So without worrying about slides, that's what's going to be inside of that main function in the guest for you. And what that means is that if I have a receipt, I already know that it's a composite because I know that you successfully ran a program which, if it ran successfully and didn't panic, must have had 2 integers as inputs that were not 1, that multiplied together. And then you can read that public value out of the journal when you're done. And so that's what the guest program contains. Thank you for that question. That's really...
So ultimately, what's important is no call and panic statements basically says, what can be trusted, basically. If none of these panic statements triggered,
Yeah.
we proved that all the opposites happen.
Yeah, exactly, exactly. And that's where I'm talking about occasionally you can use a panic in that way if you don't care about why it panicked, right? If you're just wanting to say, if you have this receipt, then you know it didn't panic here, and make that a condition of its successful execution, then you can throw panics in where usually that wouldn't be a good idea.
But if you want to prove the inverse, you shouldn't use them.
That's right. Yeah, yeah, yeah.
In lieu of the slides, I could pass out these booklets.
Oh,
Maybe you could use those.
I appreciate you so much. Yeah, yeah, spread the good word of zkVM.
Just give you one of these first, so that maybe if you want to.
Oh, follow along. And, you know, unfortunately, the next few slides are actually the ones that have nothing to do with what's in this booklet, but it's all right. It's all right. We're going to keep rolling. Okay. So, oh my goodness. All right. You know what? Okay. I want to encourage everybody. I'm going to be real careful here. I want to encourage everybody to try our bounties. So now that you've had a chance to take a look at what you can write in the guest zkVM, I want to just first check, are there any other questions? Anybody else want to?
Maybe answer the Bonsai app actually afterwards. Bonsai, that's on Solidity. It's
So none of our bounties right now are going to be using anything with Solidity. No, Bonsai is not going to be publicly available for this. We're just writing programs for the zkVM for it. So we did briefly make it available, but we're going to hold off for a little while longer before making that public. But we do encourage you to write programs for the zkVM, and once we have the proving service available, you'll be able to submit those and run them on the proving service. So that's the state for now. Yeah. So I'd be happy to answer any technical questions aside from when is it coming out. That's true. It's not a technical question. Could I? Oh, what is Bonsai? Totally. I have a lot of pictures on the next slide, and I'll get to that one in just a second. But if anybody has zkVM questions, I just want to make sure we're all good on the basics before I go to the service that runs the basics. But thank you for asking that. Just 1 second. I think I saw a hand behind. Yeah.
Is it just the guest code that needs to be RISC-V compatible, or does the host as well?
Oh, that's a good question. Just the guest code, but what we're able to do is Rust compiles down to RISC-V, so you get it for free. And so,
Call in or use the prover in another environment, like Boston.
if you're trying to use the prover in another environment, I mean, if you could get it to,
A lot of them is not going to work. Like,
yeah.
memory limit.
Oh, ouch, yeah.
For the prover to verify.
Okay. I thought not touching anything would work.
Another thing you can do is run, like, in your guest program can be a WASM interpreter. So you can, like, there's REST implementations of, like, WASM. So you can enable that and try to get something working as well. It's not, like, the prettiest thing, but, you know, it is a program, and after all, that can run other programs. So that's another option. You can see that in our examples, we actually have RE create enabled, so it's kind of similar.
Yeah, that might not be bad. Okay. It's just been. All right. Take 1 second here. And then I just want to add on briefly to that, which is that the prover has the limitations we just discussed, but verification can happen anywhere as long as you can implement a verifier.
And the verifier actually is built daily on Boston.
Yeah, yeah. So already done, already in existence. Ooh. Oh, that's very exciting. Okay. I was really hoping that this part I would be able to have pretty pictures for. Yes. Okay. Now I'm really not going to touch anything. Bonsai. All right. Now we're on to the next section here. I just want to talk briefly about our upcoming proving service. We're all really excited to see this launch. We're still working on it pretty heavily. What it's going to be is it's going to be a network that's designed to let you build kind of a new class of zero-knowledge applications. It's massively parallel, it's chain agnostic, and it's also, like the zkVM, general purpose. So in order to enable this, we built a pretty modular architecture that can be composed to let the network interact across any chain, across any protocol. So what we have right here is an example that uses blockchain, but I just want to point out your program does not have to come from the blockchain. This is not a blockchain-specific application or service. So we're going to provide an API. You'll be able to interact directly with Bonsai without necessarily coming from the chain. And you'll also be able to upload your own binary files for us to execute at your request there. And you'll be able to directly upload completed proofs. So although this example here is going to use Solidity for Ethereum, we will be expanding support to other chains. So please just take this as a working example. Because it's pretty modular and composable, it's easier to concretize here. But if you have another example, particularly off-chain, we're still really excited to build this out for you. So starting with the blockchain example. We're going to start out here with a contract that asks us to go ahead and run your program in a zkVM. That contract, in our first working example, goes to our bridge contract, which not a classic bridge in the blockchain sense, but just something that handles API interactions. It's going to interact with our API, and then we'll send the proof request to a request pool. We're going to run your program, send those inputs to the guest zkVM, and so just like the example we took a look at, we're now going to be running a guest zkVM program. Just like the example we looked at, the zkVM program is going to generate a receipt, and where this differs is we're going to start passing the receipt on to our proof rollup system, and we'll take care of this for you. And then, at the very end, we're going to verify the receipt and send the results back to your contract. And now, or tell your contract where to find the results. And then your contract will be able to use the program's outputs. So with this example, just writing in Solidity, you can call out, get results, and do an off-chain computation, which we're pretty excited about because there's quite a lot of things that you wouldn't necessarily want to do on-chain or that are currently kind of limited on-chain. But just to reiterate, this example uses Solidity for Ethereum. This example is an on-chain example, but this is not a blockchain app service, specific service. It's a ZK proving service. And if you're interested in joining the waitlist, hopefully this will not glitch out for long enough for you to take a picture on your phone. Awesome. I'll give you a second here. Okay. It'll take a second until I see all the phones go down. Okay, fantastic. And then I just want to check, in the back, you asked about Bonsai. I want to see whether your initial question got answered, or if there was a more specific one that you were looking for. Okay, cool. Yeah. That is a pointy question I am not prepared to answer at this moment. I'm not going to answer questions about money or time. I should have been more specific. Any other questions, specifically just about engineering?
Does the guest have any shared state? Like, if I want to do like a secret auction or something, does it get to see who the winner is and keep track of some shared state, or is it just like stateless?
So give me your auction. Walk me through your auction example.
It's like a secret auction, and no one knows who the winner is, but it's keeping
Right.
track of the current.
Right. Oh, so whether you could have statefulness inside of that?
Yeah, it's stateless, I'm guessing. It's not like there's some shared state.
Yeah, it's one, it executes, it's done executing, it produces a receipt out, so in that regard, it's pretty modular. Totally.
So that's where the blockchain keeps the shared state. Where like in that blockchain example, you would have some shared state updating some numbers there.
Yeah, I'd probably have to, And anybody want to tell me, anybody engineer here want to tell me otherwise? For the, oh,
Stateless, so you provide
great.
any information as it goes.
Awesome. Just want to make sure I'm telling the truth here. Any other questions?
I have a question.
Yeah.
I'm trying to understand the journal more.
Yeah.
And I'm wondering if you could like say some examples of like what someone might commit to the journal in a project, or also like is it for inputs or like outputs? Like I don't
Totally.
understand if like the proof kind of like is part of the journal,
Right.
or like you're exposing the things that went into that.
Yeah. Because you are sharing the proof, right? And I did say that the proof was everything that was public, yeah. So I'm sharing the receipt, and the receipt functions, I'm not going to say functions as a proof. The proof is the process by which I prove it, but then the receipt says I have proven the correctness of this execution. And the receipt itself is going to tell you that you correctly executed your program, and you'll be able to see which program was executed and match it against that. So that part is the receipt itself. What the journal is for is just for anything that happens inside your computation that you consider an important result to share with other people. And that's not the computation itself, but values in there along the way. Because oftentimes a black box ends up being kind of useless unless you want to say, this ran, and assert that a program ran, and that's all you want to run, which sometimes you do, right? Sometimes you're checking the validity of something, checking the integrity of something, making sure something passes all of your requirements, right? And you've made it panic otherwise. And in that case, it's fine to just send the results, but in most cases, you are going to want to have some parts be public, right?
Maybe I can also make another more concrete example. So do you guys know that typically in digital signature we are in blockchain we are using this complicated public key cryptography based on the dictator or RSA or whatever. There are like simple way to implement a digital signature scheme which are based on hash, right? So what we do is that we use as a secret whatever string or value, right? And then you hash that and together with maybe a message. And that could be a signature. Now the problem is that you want to verify that you know the secret, which would be the pre-image, right, of your hash. And the only way to do it is you have to reveal the secret, right? So that's why typically, that scheme is not well used unless it's a one-time signature. But with this example that Kay was talking about, what you can do is that you can write the algorithm, right, in the guest code that basically just take the input, which would be your secret key, hash it, and then commit the result of the hash, right? And that would be basically the public key. And when I say commit, you write to the journal that is the public key, right? So when you verify a receipt in this way, you can always be sure that the prover knew the secret key without revealing it. And so that's another concrete example of how you can use the journal to write public input that will allow to solve many of the complications due to modern public key cryptography.
Totally. And I want to point out that publicly sharing the hash is a pretty common pattern, a pretty common, not design pattern, but a pretty common pattern when you're writing a program for zkVM. So to use another example, if I was playing the game of Battleship, I'm not a, for those who aren't familiar, you put the ships on the board, somebody else guesses a place, it either blows up your ship or it doesn't. If I want to make sure and attest to the fact that I haven't moved my ships around, that I'm using the same board, I might commit a hash of the board in a program that checks whether you sunk my battleship. So, and then we have another example in our examples repo that's a Wordle example where we make sure that we're actually using the same word and not shifting the word out from under you, which would be a pretty mean Wordle game.
So would those be like things that are in the journal, is like showing that you're using the same word?
Yeah, it's going to hash the same way every time.
Thank you.
Yeah, no problem. And thank you for asking that. That's a good, understanding which pieces to share ends up being really, really critical for writing a good program. Any other questions? All right, in that case, I want to open this up and say, does anybody have any projects they're interested, projects they're excited about, things they're interested about building and want to know more on? And I can either answer it or connect you to one of our engineers in the room. Yeah.
I was going to just say I'm building something, but someone wants to join. I just wanted to say what it was.
No, this is great, that you're building something.
Cool, yeah, I just wanted to play around with building an order book matching engine.
Awesome.
Here this weekend, so if anybody's interested, come out or just...
Fantastic. Okay, so for folks who didn't hear, or folks who are remote, somebody's building an order book matching engine and would love to have people reach out. Any way that they should get in touch with you if they're remote, or?
I can put my name on the thing.
Perfect. Anybody else? Okay, cool. In that case, I just want to check in with our Bonsai team. Anything else you'd want to chat about Bonsai on? Anything else you'd want to share? Awesome. All right, in that case, I want to open this up and either give you time back or encourage you to stick around and start working on projects. We do have a pile of engineers here, so if you want to get started, we'd be happy to help you out and just spend a few minutes getting you going and going past any of the initial blocks you might encounter. So thank you. Really excited to share this with you. I hope you all have a really great hackathon.